Hey everyone, and welcome to The Explainer. So today we're going to do something a little different. We're not just going to solve a coding problem. Nope. We're going to go on a journey, the journey of an idea. We'll see how you can start with a really simple, almost obvious solution, and then step by step, refine it and polish it until it becomes something, well, brilliant. Let's get started.
All right, so let's put you in the driver's seat. You're standing at the bottom of a staircase. The rule is simple. You can take one step or two steps at a time. The question is, how many different ways can you get to the top? Now, if it's, say, 3 steps, you can figure that out pretty easily, right? You could go 1, 1, 1, or 1 then 2, or 2 then 1. 3 ways, easy. But what if it's 10 steps, or 45? Suddenly, it's not so simple. This is the famous climbing stairs problem, and trust me, it's the perfect playground for learning how to think like a programmer. Okay, so here is the big aha moment, the key insight. To get to any step, let's call it step N, what was your very last move? Well, it had to be one of two things, right? You either took a single step from the stair right below it, N-1, or you took a double step from 2 stairs below it, N-2. That's it. There are no other options. So the total number of ways to get to stair N is just the ways to get to N-1 plus the ways to get to N-2. And if that little pattern is ringing a bell, it should. That's the Fibonacci sequence, right there in disguise. Okay, so we have our core idea. And when you're starting out, what's the most natural thing to do? You just translate that logic directly into code, right? No fancy tricks, just a straight-up implementation. This is what we call the brute force approach. And you know what? Recursion is like tailor-made for this. We can literally write a function that says, hey, to find the answer for n, just call me again for n-1 and n-2 and add those two answers together. It's beautiful. It's so clean, so elegant. It perfectly mirrors the logic we just figured out. You write this code and you think, yes, I'm a genius, nailed it. But, there's a catch, a big one. So here's the trap. Let's say we want to calculate the ways for 5 steps. Our function goes, okay, I need the answer for 4 and the answer for 3. Simple enough. But then, to get the answer for 4, it says, okay, I need the answer for 3 and the answer for 2. Wait a second. Did you catch that? We're now calculating the answer for 3 steps twice. And this is just for 5 steps. As that number gets bigger, this problem doesn't just grow, it explodes. You get this massive tree of the same calculations being done over and over and over again.
And this is what happens. You run your beautiful code, and you get this big, red, angry message, time limit exceeded. Your program just gives up. It's so busy redoing the same work that it can't finish in a reasonable amount of time. So, our brilliant first idea is actually a dud. It's elegant, but it's fatally flawed. So, how do we fix this?
Well, we go right to the source of the problem, right? The issue is that our code has a terrible memory. It keeps recalculating stuff it's already figured out. So what if we could just give it a memory? This question right here is the game changer. What if our function could remember the answers it already figured out? It's like giving your function a little notebook or a cheat sheet. Before it dives into a heavy calculation, it first takes a peek at its notes and asks, hey, have I done this one before? And if the answer is yes, bam, it just grabs the answer instantly. No extra work needed. This brilliant little trick is called memoization. And you can see how small a change this actually is in the code. On the left, that's our original function just blindly calling itself again and again. But on the right, look at that. It's almost the same, but we've wrapped it in a simple check. Is this answer in my memory? If it is, great, just return it. If it's not, okay, do the calculation, but, and this is the most important part, before you return the answer, you jot it down in your memory for next time. That's it. Now, that expensive calculation for, say, climb 3 only ever happens once. So memoization is a huge improvement. It works, it's fast, but it's still what we call a top-down approach. We start with our big goal, like 45 steps, and we break it down into smaller and smaller problems. But what if we flip that on its head? What if we completely reframed the problem? Instead of starting at the top and working down, what if we started at the bottom and built our way up? This is exactly what tabulation is all about. It's a bottom-up approach. I mean, think about it. We already know the answer for the first few steps, right? For step 0, there's one way. You're already there. For step 1, there's one way. Just take one step. So if we know the answers for 0 and 1, we can figure out the answer for step 2. And once we have that, we can figure out step 3 and then step 4. We just build our solution from the ground up,
one stair at a time. And a table like this is the perfect way to see it in action. So we start by just filling in what we know. Step 0 gets a 1, step 1 gets a 1. Those are our base cases. Now, for step 2, we just look at the last 2 entries and add them up. 1 plus 1 is 2. Easy. For step 3, we look at 2 and 1. That's 3. For step 4, 3 plus 2 is 5. And we just keep going. We just run a simple loop, filling out this table all the way to our final number. No more recursion, no more crazy function calls, just simple, clean addition.
Okay, this is great. I mean, this is a really solid, fast, and easy to understand solution. But if you want to think like a top-tier engineer, you never stop asking one question: can we do better? Right now, we're building this whole table, this whole array, to store every single answer from 0 all the way up to n. But do we really need all that information?
So let's really think about this. Go back to that table. When we were calculating the answer for, let's say, step 4, what numbers did we actually look at? Well, we only needed the answers for step 3 and step 2. That's it. We didn't care about the answer for step 1 or step 0 anymore. They were totally irrelevant to that calculation. And that's true for every single step. At any given moment, you only need the 2 results that came right before it.
And that is the final key insight. We can just throw the whole table away. We don't need it. All we need to keep track of are the last 2 numbers. Just 2 simple variables. And that's it. That is peak optimization for this problem. Think about the journey we've been on. We went from an exponential solution that timed out to a linear time solution, and now we've taken the memory from a whole array down to literally just 2 variables. Okay, so let's see how this actually works in practice. It's super simple. We start with just 2 variables. Let's call them prev and cur. We'll set them both to 1, representing the answers for step 0 and step 1. All right, now to get the answer for step 2, we just add prev and cur. So 1 plus 1 gives us 2. That's our new current value. And here's the magic trick, the little shuffle. Our old cur, which was 1, now becomes the new prev. And that result we just calculated, 2, becomes our new cur. See how they just leapfrogged over each other? Now we just do it again. For step 3, we add our current prev and cur. So 1 plus 2 equals 3. And then we do the leapfrog again. The old cur, 2, becomes the new prev, and our new result, 3, becomes the new cur. We literally just repeat this super simple add and shuffle process until we hit our target number. It's unbelievably fast and uses barely any memory at all. So let's step back for a second. What was the point of all this? Yeah, we solved the stair problem, but what we really did was uncover a powerful blueprint for solving problems in general. This is a mental model you can pack in your toolkit and use on so many other challenges. And here it is, your 5-step plan. 1, always start with the simple brute force idea. Just get it on paper. 2, hunt down the waste. Where are you doing the same work over and over? 3, fix that waste by giving your code a memory, using memoization. 4, try to flip the problem on its head. Can you build the solution from the bottom up instead of breaking it down from the top? That's tabulation. And 5, the final polish. Be greedy with your memory. Ask yourself, do I really need to store all of this stuff? And optimize your space. So now you have this toolkit. And the thing is, this process, starting simple, finding the flaws, remembering your results, reframing the problem, and then optimizing, that's the heart of problem solving. It's not just for code. It's for, well, everything. So my question to you is, what else can you solve with this? What other big, messy problems out there can you conquer just by taking that first simple step and then iterating your way to brilliance?